Every morning, without fail, the sun rises. It has done so for every civilization that has ever existed. It shone upon the pyramids, upon the Roman Empire, upon the first forests, the first oceans, even the first single-celled life on Earth. To us, the sun feels eternal, permanent, unchanging. It is the one thing in our sky that seems impossible to imagine without. But the universe does not recognize forever. Stars are born, they live, and eventually they die. Our sun is no exception. Right now it is almost exactly halfway through its life. Its fate was determined long before Earth even existed. One day it will grow so large that the inner solar system will never be the same again. Mercury will disappear. Venus will vanish. Earth will become an unrecognizable world. And after all its brilliance, the star that made life possible will quietly fade into darkness. This is how the sun will die. To understand its ending, we must first understand why it shines at all. The sun is not burning like a giant fire. There is no oxygen, no flames, no coal being consumed. Instead, deep within its core, the pressure is almost beyond imagination. Above every point in the center, hundreds of thousands of kilometers of hot plasma press downward. Temperatures climb to around 15 million degrees Celsius. Under those extraordinary conditions, hydrogen nuclei collide with such violence that they overcome their natural electrical repulsion. They fuse together. 4 hydrogen nuclei become 1 helium nucleus. A tiny fraction of their mass disappears, not because it is destroyed, but because it becomes energy. Einstein described the relationship with a simple equation: E equals mc squared. Every second, the sun converts roughly 600 million tons of hydrogen into helium. About 4 million tons of mass become pure energy. That energy begins an astonishing journey. A single photon created inside the core may take hundreds of thousands of years, perhaps even longer, to work its way through the dense interior. Only after finally escaping the surface does it race across space. 8 minutes later, it reaches Earth. The sunlight warming your face today began its final journey from the sun only minutes ago. But the energy itself may have started traveling long before modern humans existed. For billions of years, fusion has maintained a perfect balance. Gravity pulls the sun inward. Fusion pushes outward. Neither side wins. The star remains stable, not growing, not shrinking. A magnificent equilibrium. But equilibrium is not permanence. Every second, the core loses hydrogen. Very slowly, its fuel supply changes. And one day, the balance will break. Fortunately, not anytime soon. The sun formed approximately 4.6 billion years ago. It is expected to remain on the main sequence, its current stable stage, for roughly another 5 billion years. Human history occupies less than the final fraction of 1% of the sun's lifetime. Civilizations have risen and fallen, without the sun changing in any noticeable way. To humanity, it appears immortal. To the universe, it is middle-aged. Long before the sun reaches its final chapter, Earth itself will begin to change. As hydrogen disappears from the core slowly contracts. That contraction raises temperature and pressure. Fusion becomes more efficient. The sun gradually grows brighter, not dramatically, but steadily. In roughly 1 billion years, it may shine about 10% more brightly than today. That small increase could have enormous consequences. Earth's climate would continue warming. The oceans would begin evaporating. Water vapor, a powerful greenhouse gas, would trap even more heat. The process would accelerate. Eventually, the seas that gave birth to life would disappear into the atmosphere. Ultraviolet radiation would break water molecules apart. Hydrogen would drift into space. Earth would become dry, hot, and increasingly hostile. Life as we know it would struggle long before the sun ever became a giant. By around 3 to 4 billion years from now, the surface could resemble something closer to present-day Venus than the blue world we call home. The final transformation begins when the core can no longer fuse hydrogen. The central furnace goes quiet. For a brief time, gravity finally gains the upper hand. The core contracts rapidly. Temperatures soar. Hydrogen surrounding the core ignites in a shell. The outer layers respond dramatically. The sun begins to expand. Slowly at first, then relentlessly. It enters the next stage of its life, a red giant. The name can be misleading. The surface becomes cooler, giving the star a reddish color. But the total energy released increases enormously. The sun grows brighter, while swelling to extraordinary size. Mercury, the closest planet, will almost certainly disappear, consumed by the expanding atmosphere. Venus will almost certainly share the same fate. Then comes the greatest uncertainty, Earth. For decades, people often stated confidently that Earth would simply be swallowed. Today, the picture is more complicated. As the sun loses mass, its gravitational pull weakens slightly. Earth's orbit would slowly drift outward, but at the same time, the sun's enormously expanded outer atmosphere would create drag. Tidal interactions between Earth and the swollen sun would also influence the orbit. Current models suggest that Earth may well be engulfed, though the exact outcome depends on details of the sun's mass loss and expansion that are still being refined. In one possible future, Earth spirals inward and disappears inside the sun's outer layers. In another, it narrowly escapes physical engulfment, only to be left as a scorched, airless, molten world. Either way, the result is effectively the same. The Earth we know will not survive. By then, the atmosphere would already have vanished, the oceans long gone, the continents partially melted. No forests, no clouds, no life, only a silent world, orbiting or falling into its dying star. Eventually, the temperatures inside the contracting core become high enough for helium fusion to begin. Helium nuclei combine, producing carbon and oxygen. For a relatively brief period, the sun finds a new balance. But unlike hydrogen, helium is limited, and our star is not massive enough to continue fusing heavier elements. It lacks the necessary gravity. Unlike truly massive stars, the sun will never forge iron. It will never explode as a supernova. Its ending will be quieter, gentler, and in many ways, more beautiful. As the remaining nuclear reactions fade, the sun begins shedding its outer layers. Not all at once, but gradually. Shell after shell of glowing gas drifts outward into space. For thousands of years, those expanding clouds create one of the universe's most beautiful sights, a planetary nebula. The name is misleading. These glowing shells have nothing to do with planets. Early astronomers simply thought they resembled tiny planetary disks through small telescopes. In reality, they are the atmosphere of a dying star, illuminated from within like a cosmic lantern. Every atom of carbon, nitrogen, and oxygen drifting through those clouds will eventually mix with the galaxy. Some may one day become part of another star, another planet, perhaps even another living world. The sun's death will help create future beginnings. At the center of the expanding nebula, one object remains, the exposed core, no longer producing significant fusion, about the size of Earth, containing roughly half the sun's original mass. This is a white dwarf. Do not let the name fool you. A white dwarf is unimaginably dense. A single teaspoon of its material would weigh several tons on Earth. Gravity has compressed matter to astonishing extremes. The atoms themselves are packed together in ways impossible under ordinary conditions. When the sun first becomes a white dwarf, its surface will still exceed 100,000 degrees Celsius. It shines not because fusion continues, but because it retains the immense heat built up during billions of years of nuclear burning. Slowly, very slowly, it begins to cool. Unlike ordinary stars, a white dwarf possesses no new source of energy. Every year, every million years, every billion years, it simply radiates away the heat it already contains, growing dimmer, redder, colder. Its cooling is almost unimaginably slow. The universe itself is not yet old enough for any white dwarf to have completely cooled. Which brings us to the final stage, the black dwarf. A black dwarf is not an observed object. It is a prediction, the ultimate fate of every white dwarf. After trillions upon trillions of years, perhaps even longer than a quadrillion years, the remaining heat would finally dissipate. The star would no longer glow. No visible light, no warmth, only a cold, dark, dense remnant. The universe has not existed long enough for even one black dwarf to form. If they ever do, they will appear in an age so distant that almost everything familiar will already be gone. Long after galaxies have changed, long after star formation has largely ceased, long after the night sky becomes almost unrecognizable, the sun's final chapter has not yet begun. In fact, humanity exists astonishingly early. The sun still has approximately 5 billion years of stable life remaining. That is longer than the age of Earth today. To place it in perspective, if the sun's entire lifetime were compressed into a single 24-hour day, human civilization would occupy only the final fraction of the last second. Every empire, every language, every discovery, every war, every piece of music, every person who has ever lived, would fit inside a moment too brief to notice. Our greatest concern is not the death of the sun. Civilization faces many nearer challenges. Earth itself will change long before the sun's final expansion. Humanity may survive. It may leave Earth. It may spread to other worlds, or it may disappear entirely long before the sun reaches old age. The star's death is not our immediate future. It is our distant inheritance. Yet there is something strangely comforting about that. The sun is not dying today. It is doing exactly what stars have done for billions of years, living according to the laws of physics. No tragedy, no punishment, no drama, simply time. Everything in the universe changes. Mountains erode, galaxies collide, stars are born, stars die. Even the brightest light eventually fades. And perhaps that is precisely what makes this moment extraordinary, because right now, the oceans still shimmer beneath the morning sun. Forests still grow, birds still sing, children still play beneath its warmth. Every sunrise you have ever seen has come from a star, still in the prime of its life, a star that has quietly supported nearly every living thing that has ever existed. Tonight, as darkness falls, remember that the sun has not disappeared. It is simply shining on another part of the earth, doing what it has done for billions of years, holding gravity and fusion in perfect balance, patiently, silently, waiting for a future so unimaginably distant that 5 billion years from now, its final sunset will still be waiting. And when that day finally arrives, the star that gave us life will leave behind one last gift, the atoms forged in its heart, scattered across the galaxy, waiting to become the beginning of someone else's dawn.